Today's lesson is on CSEC physics. I am Pethorn Dawkins. Alright, so good morning students. We are going to be talking about optics, reflection, refraction and lenses. As it is right now, you're sitting at home and you're able to see me, and I'm not seeing you, but you're able to see me, and you're wondering, well, you may have asked the question, how is it that truly your eyes are able to pick up on images? It's simple and it's complex, but I'm going to try to see if I can make a balance out of it. So here I have here picture put up. Reflection, refraction and lenses. Hopefully we can get through all, but at least we'll be starting off with reflection and refraction. In the syllabus, you would have been aware of this under waves and optics. Now, with regards to this topic, reflection and refraction will come up. And the diagram illustrates here reflection and refraction. But we're going to make sense of all of this as we go along, so fret not. But before we really go into what is reflection and refraction, we must really now look at what reflects and what refracts, and which is that? Light. So there are certain properties of light that you must be aware of. First one, light travels in a straight line and at a speed of 3 times 10 to the 8 meters per second. We're talking about 300 million meters per second. That's blind fast. It does not need a material medium in which to travel, meaning that a vacuum. Light comes from the sun to us, it travels through a vacuum. There is nothing in outer space. It's transverse in nature. Transverse meaning, for persons who are aware of the wave profile, that's a transverse wave. Particles move up and down as the wave travels across. So it's transverse in nature. The other one is longitudinal, but that's not light, so we're not concerned about that. It demonstrates the phenomena, big word, of reflection, refraction, diffraction, and interference. So we're going to look at the first two. This lesson doesn't look at the last two. And passing through a prism, which is essentially a glass triangle-shaped material, it separates into its component colors to produce a spectrum. Now that ROYGBIV can be mentioned, or it's an acronym, we can call it ROYGB, just remember that. It stands for the 7 component colors for which light is basically composed of. Red, orange, yellow, green, blue, indigo, and violet. And a picture here shows us, in actuality, what white light or even sunlight would look like if you pass it through the glass prism. So we shoot light through it because of refraction taking place. As we look at, the light goes in and the 7 colors come out. And if you look closely, you can see the red, orange, yellow, green somewhere there, blue, indigo, and violet coming out there. So there are 7 component colors that come together to actually produce white light. Now, let's look at refraction a bit. This is where wave energy bounces off a surface that does not absorb it or allow it to pass through. So one, the surface that it hits, for it to reflect, it cannot be absorbed by it. And 2, it cannot pass through it. So for reflection to take place, no absorption, no passing through. Second thing, the manner in which the wave or the ray is reflected is governed by laws of reflection. You know, in physics there are always some laws. Persons come up with laws and whatnot. So don't sweat it. There are 2 laws. The 2. First law, the angle of incidence of a wave or ray is equal to the angle of reflection. We'll get to that in a bit. The incident wave, the normal line, and the reflected wave all lie on the same plane. Now, what do I mean by this? Take this as a plane surface. This has been the wave that comes in on a plane surface. Surface is here and it's flat. This will be the normal, this will be the reflected wave. So all of them now lie on a flat surface. When they move to maintain a flat surface. That's what the second law really means. Alright, so if it's like this, it will be like that. It can't deviate from the flat surface any at all. Alright, so that's what the second law talks about. The first law is essentially this. Now an incident ray or wave can be drawn as a straight line. When it hits a surface that does not absorb or allow it to pass through, it bounces off. Now the angle that ray makes with a, what do you call an imaginary line, this imaginary line drawn dotted is the normal line. It's just an imaginary line that they came up with to just measure the angle. So this line is a reference line to which the angles are measured. So the incident ray hits the surface, this is the angle of incidence. as labeled here. The ray that comes off, which is a reflected ray, that angle is the angle of reflection. So angle of incidence from the normal to the incident ray, angle of reflection from the normal to the reflected ray. So the first law that we mentioned before, being equal, means that whatever this angle is from the normal, the reflected ray will have the exact same angle. Alright, so that's what the first law states. And the second law, as I mentioned, all of this line, that line, this line, they all lie on the same plane. Alright, so that's the essence of reflection right there. Now, reflection produces images. When you look in the mirror, you see yourself. I hope that you like what you see. Good? Now, with regards to the image that is produced, the image has certain properties. Image produced by plane mirrors, and a plane mirror is something similar to this, and it's a mirror surface, have a number of properties. One, the image produced is upright, meaning that if you're standing upright, you'll see yourself as upright. If you're upside down, guess what? Image is going to be upside down. The image is the same size as the object. Sometimes when you look at certain things, when it deals with optics, things look smaller or larger than they actually appear. No, when you're in a plane mirror, the image will be the same as it is. So for biology students, you know about magnification. Magnification is basically how much greater or smaller the object is than the actual thing. So if the same size is for image and object, then the magnification is 1. Next property. The image is the same distance from the mirror as the object appears to be, meaning the image distance is object distance. So here's the thing. I am currently right now a certain distance from this camera. Say this camera was a mirror. Whatever distance I am from the camera, that is the object distance. Inside the mirror, you would see yourself at the same distance away from the mirror. So from the mirror to the object, yourself, that would be the object distance. What you see in the mirror, that distance from the mirror to what you see is the image distance. Got it? So the same distances will be with regards to this property. Next property, the image is a virtual image as opposed to a real image because the light rays do not actually pass through the image. Now I'm going to go to a diagram to kind of explain this a bit, but basically a virtual image is one where light rays don't really come to focus on. And let's look at this. Now, here we have a female standing in the mirror. You know, the females like to look at themselves, posing and whatnot. So, this is her image. She sees her image in the mirror. Remember, light travels from an object and hits your eyes for you to see it. If light doesn't come from an object, you can't see it. Now, for her to perceive this image, it means that the light must be coming from the image to her. So the image itself, there's no light rays that originate from it, you know. The light rays actually come from light that hits the mirror, hits you, and you're able to see your image because of the light that comes from you to the mirror and to your eyes. However, what you perceive is the image behind that mirror because if you trace it back, it will appear as if it is coming from here. But in reality, it is actually going this way, hits here, and comes back. Same thing for your leg. It goes up here, it hits here, and it comes back. So this is not real. It's virtual. But that's what you perceive. So you tell yourself that, well, that's real, but it's not real. Virtual images are ones that light rays don't originally or actually come from. Alright? So real images, light actually comes from it. You would be real. Light comes from it to you and you see yourself, but you perceive a virtual image. Got it? Good. This also shows a little bit of it. A point is here. If you're viewing this point in a mirror, if you're over here and you view this point, you actually see the point down here. Does not mean it is actually here. This is real, this is virtual. This is object, this is image. So the light from this object bounces off the mirror, goes, bounces off the mirror, goes. So you as the observer over here will not see this, you'll see that. But this is real. Got it? Good. Let us move on. Refraction of light waves. Now, this is a different thing now when it comes down to light waves. Before we looked at light waves bouncing from a surface that doesn't absorb it, doesn't allow it to pass through. That was reflection. Now we're going to look at a little different thing that happens to light when it actually passes through a material. So, refraction, and don't mix up the terms. Reflection is bouncing from surface that doesn't absorb or doesn't pass through. Refraction is this. It is the change in direction of travel, fancy word deviation, of a wave or ray as it travels between two media that are of different optical densities. Optical densities are basically, it allows light to pass through it, but some just fight it. So if you consider like air, yeah, there's not much opposition to light passing through air. If you consider water, well, water is a lot denser than air, so there's going to be some opposition to it. If you consider glass, if you consider diamond, anything that is transparent that allows light to pass through it, now will not necessarily have light passing through it the same extent. Some allow it more freedom than others. So that's what we mean by different optical densities. Now, the manner in which a wave or ray is refracted is governed by two laws of refraction. Again, we look at the laws. The incident ray, the normal ray, and the refracted ray all lie in the same plane. Remember that thing that I showed you a while ago? Right. It's the same thing that applies here. Incident ray, normal, refracted ray, all lie on the same plane. Now here's the difference with refraction. The ratio of the sine of the angle of incidence, it's a bit wordy, work with me, to the sine of the angle of refraction gives a constant value called the refractive index between two given dissimilar optical media. Wow, what a word, mouthful. Essentially, and we're going to look at the diagrams. There's an angle of incidence just like reflection. But instead of just looking at the bare angle, they sine, and by sine we use in the trigonometrical ratio, sine, cosine, tangent, right? So when we sine the angle of incidence, and we sine the angle of refraction, refraction, then the ratio, and by ratio I mean that we divide, so it's the sine of angle of incidence at the top, sine of angle of refraction at the bottom. When you divide those two, then it will give you a value. If you change the angle of incidence, the angle of refraction will change. When you sine those two values, guess what? You get the same value coming out. This constant we call the refractive index. Dissimilar means that they are not the same. Optical media, you know that it allows light to pass through, but not to the same extent. Now, this is important. This is also known as Snell's law. So, if asked, what is Snell's law? This is one statement you can give. You can summarize it in your own way, but essentially what should come out, sine, angle of incidence, sine, angle of refraction, divided or ratio. That is Snell's law. Now, let's look at refraction from a diagram standpoint. Here we have the incident ray. Now, normally, if this was reflected, it will be bouncing off this point here. But here we have a situation where this boundary is not one that will reflect. It will actually cause it to go into the next substance or medium or region. Now, when these two substances are of different optical densities, then the line that it was traveling at will no longer be maintained. This will now cause the ray to move away from it. It can move towards the normal or away. We look at that. But just know, once it is moving from one material to a next, and they have different densities, then it will be bent towards or away from the material. Once this bending takes place, then you have refraction occurring. Now, with regards to the refraction phenomenon, a wave or ray that is refracted from one medium to another can either increase in speed, move faster, or decrease in speed. As I said, light will travel the fastest in when there is nothing present, which is a vacuum. Air is approximately like a vacuum. So, what we have is that air will allow light to travel the fastest. When it goes to water or glass or any other optical material, the speed will change. And as a matter of fact, more dense, slower speed, as you see down here. Alright? So, it can either increase in speed, move fast, or decrease in speed, move slow. If the wave increases in speed, then the direction of travel bends away from the normal. If the wave decreases in speed, then the direction of the travel bends towards the normal. So, as I was saying before, From less dense to more dense, it slows down, it bends towards the normal. From more dense to less dense, alright, here's the diagram, good. So, light bends as it goes from one substance medium to another because it changes speed. Air to glass, less dense to more dense, it bends toward the normal. Glass to air, so they have flipped the script. Glass to air, more dense to less dense, it bends away from the normal. So this is a fraction, that's also a refraction. This is slowing down, that's speeding up. Bending towards normal, bending away from normal. They go together, alright? So compare the bend to the normal, just like reflection. Light bends towards the normal when it goes from a less dense to more. Light bends away from the normal when it goes from a more dense to a less dense. Alright? So that's what refraction is talking about there. Now, with regards to illusions of refraction. Refraction creates certain illusions that persons sometimes see and wonder, well, yeah, what's happening there? Magic or obeah or whatever they want to call it. But no, it's just science in play. Now, when you put a straw or a pencil in water, based on your line of sight, you may actually see that pen or straw has been broken. Is it indeed broken? No, because if you do it your own self, you'd realize that you put it in, it's broken, you take it out, it's okay. Alright? So a bent or broken appearance of the straw is actually because of the diffraction phenomenon taking place. Alright? And we'll look at it because the slide deals with it. But just know, once you see this, it's not any great magic trick. It's just science at play. Now, another cool effect of refraction is this thing. They call this a mirage. M-I-R-A-G-E. Driving on a long stretch of road, asphalt before you, sunny, hot day, and all of a sudden you're looking way out in front and you see as if the road itself becomes glassy, or it seems like, you know, it's watery or it's puddle. Yeah, I know probably persons would have seen this because it's something that is common. Once you're driving on a hot day and road is out in front of you, you may see this come up. And you may wonder, well, water is on the road, oil is on the road. No, it's actually this refraction thing taking place. What really happens is that the surface is hot. The air above it is cool. Because the surface is hot, it heats the air next to it. The air that's above doesn't get heated as much. So what we have is two different layers of air due to their different densities. Hotter air is less dense, cooler air is more dense. So because of this region of cool air, hot air, when light hits there, it actually bends. So when the light is bent and it is sent back, it actually appears as if light is being reflected from the road surface. But really it's refraction. And once light touches your eyes, you're going to see a reflection of whatever the light is saying. So that mirage is actually because of refraction taking place at the surface nearest to the road. Alright, so the next time you see it, don't think that it's actually something where there's a mirror out there or water out there. No, it's refraction that is actually taking place. So, an explanation to why the straw appears bent. This is the observer. A shape given an eye there. Virtual image observed by refraction. Now, remember that whole virtual thing that we talked about? Yeah. Your eyes can only perceive what light enters it. But where the light is coming from may not necessarily be along a straight line. So what we have is a situation where this is the actual position of the fish, or the pencil for that matter. And when the light rays are coming from it, the minute it hits that boundary between water and air, then we have bending taking place and then it reaches your eye. But your brain will tell you light travels in a straight line. So therefore, you will perceive the fish as being there. But in reality, it's actually down there. Cool, right? Yeah. So that's what refraction does for us. Now, here's an equation. They didn't have one for reflection, but they do have one for refraction. The CSEC syllabus will tell you about n. And n being, there's another way of stating it, but they have stated it in one way. The velocity of light in a vacuum, speed of light in a vacuum, which is the fastest it can travel, 3 times 10 to the 8 meters per second, over the speed or the velocity of light in that medium. Alright, there are other ways to state it as we look at, but you can state it from this point of view. So n being the refractive index or index of refraction can be found by dividing the velocity in a vacuum by the velocity in that medium. And it gives the equation there. Another way of stating it is to say, because right here you can see it, equivalently sine, that's theta 1 over theta 2. Theta 1 is here, theta 2 is the other one. So that's essentially, they're comparing the angles between the two media. Alright, so they can compare angles, they can compare speeds. Whichever way you look at it, it will give you the refractive index. Now this general equation here is just like that. I'll get to that when we work on the question, but just know that this is the general equation for refraction. This Ni is the refractive index of the first medium, Nr is the refractive index of the second medium, sine theta I, angle in the first, sine theta R, angle in the second. Alright? You can research this, you can go in, and you can find this easily. Just know that they are comparing angle of incidence to angle of refraction. Refractive index in one to the refractive index in the other. Once they compare these two, then you're looking at how now light will behave when light is refracted. Alright? Now, let's see if we can look at a question here. It says, Figure 1 shows light passing through a rectangular block. Important features of the arrangements are labeled A, B, C, right, C is there, D, and E. Now for persons who have done this lab, it should be a lab that you would have done in CSEC under refraction, right? This would be the glass block or the perspex block. This would now be a ray diagram where you'd put pins or something that shows how light travels. These are angles that you've measured, and this is the line that the ray would travel if the block wasn't there, and this is the line that the ray actually travels because of the block. Alright? And of course you can interpret what this is based on what we have looked at. Now, with regards to labeling the parts of figure 1, it asks you for A, B, C, D, and X. So we have A here, B here, C here, D is here, E is here, and X is there. Now, with regards to A, you must identify A as being, come on, you know it, the incident ray. Alright, because that's the ray that comes in there. B, based off the diagram, is that reflected or refracted? Remember, reflection is bouncing off from a surface. Refraction is when it actually goes from one material to another. So since B doesn't go into the glass but comes back off the surface, then this is now the reflected ray. Alright? So don't confuse that. C is that line that is perpendicular or 90 degrees to the boundary. So you can just jump and say, alright, this should be the normal, of which it is. Or you can say normal line. Normal or normal line, that suffices. Alright. For D, we have a refracted ray there. But we can call it the first refracted ray. Alright, because a refraction takes place again, because here we have refraction, and remember, air to glass, less dense to more, it bends toward the normal. Glass to air, more dense to less dense, it bends away from the normal. So we have E being the second refracted ray. Alright, and X, we have a displacement taking place because it was shifted away. So we call that now a lateral. Lateral means sideways displacement. Alright, that's what X represents there. Alright, good. Now, it says the refractive index of the glass is 1.5. So you can state that somewhere. N of glass is 1.5. Alright? Oh, and bear this in mind. Refractive index does not have a unit. Alright? Why is it that it doesn't have a unit? We'll look at that. Determine the value of angle B when A is 60. So when you go back to that question, we need the angle of B when A is 60. Applying the laws of reflection, we see that theta I is equal to theta R, and by R we mean reflected. Alright, so if theta I is 60 degrees, then theta R, and then theta I is what? A? Good. So theta R reflected is also 60 degrees. Alright? Now, state a reason for your answer in B. Simply just say, law of reflection tells us angle of incidence equals angle of reflection, therefore the angles must be the same. Alright, calculate the value of angle D. Now for this one, we need to apply that equation that we just saw. So let me just rewrite that equation for you. We had N1 sine theta I is equal to N2 sine theta R. Alright, now for N1, this is for air. N2 is for glass because we're moving from air to glass. N1 is always taken as 1 for air, and that's sine 60 degrees. This is 1.5, and this we don't know. Alright, so once you have outlined this, you realize that there are no more unknowns. So other than this one, so what we do is that we end up with 1 times sine of 60 degrees over 1.5 equal to sine of theta R. And then of course, to get rid of this, we'd have to sine inverse, and we get the angle for theta R. And I found the answer to be 35 degrees. So essentially, this would work out to be about 0.866 times 1, that's the same 0.866. That divided, sine inverse of that, gives us 35 degrees. And we see that it is indeed in keeping with what we've been saying. Because the angle of incidence was 60 degrees, moved from a less dense to a more dense, so that means that the angle should be less because it bends towards the normal. So starting out with 60, we end up with 35 degrees as the angle of refraction. Alright, now let us look at lenses. And there's another way that lenses is stated in physics, but we're not going to look at that. We're going to look at the actual lens, and by lens we mean what light passes through to bring rays or light rays to focus. Now, a lens is an optical material that causes light rays to be refracted in a predictable manner as light passes through it. There exist two basic types of lenses. First, we have the biconvex lens, and then we have the biconcave lens. Now, all other lenses can be considered to be a combination of these two basic types. Alright, so there are other types of lenses. There's cylindrical, there's convex, concave. All kind of lenses are used for different applications based on what you want to achieve. But essentially, lenses boil down to either being convex or biconvex in nature, or concave or biconcave in nature. Now here's a diagram showing a biconvex lens. Now biconvex lens can be identified by it being fatter in the middle than it is at the ends. Just think of it like that. Alright? So it's a glass material, somewhat like a rectangle, but it is fatter or wider or thicker in the middle than it is at the ends. Now, these red lines represent light rays as they pass through the lens. So they pass parallel. When they hit this, they now are brought to focus. So a biconvex lens is also termed as a converging lens. Converge means to bring to focus. And the point that it is brought to focus is called the focal point. Go figure. Alright? Now, we have the biconcave lens. Biconcave lens, again, cylindrical shape somewhat, but it is now thinner in the middle than it is at the ends. So before, thicker in the middle, biconvex. Now we are looking at thinner in the middle, biconcave. So it curves inwards. Now here we have the light rays that pass, enter parallel, but instead of being brought to focus, converge, they spread out or diverge. And these green lines trace back now to how the light rays would actually appear to be brought to focus. So its focal point actually lies here. Now, we're going to look at some optical parameters. Big word is just basically describing how lenses are interpreted. We have the principal axis as a center line that hits the center of the lens, the optical center, the dead center of the lens itself. Optical axis, that vertical line that passes through the optical center. Focal point, where the rays come to focus, whether diverging or converging. And the principal focus is that plane where the light rays are brought to focus, or the focal point. And then the focal length is the distance from the optical axis or center to the focal point or principal focus. Alright? Same thing for the biconcave rather. Rays come in, they spread out, optical center, principal focus, focal point is here. Because remember, for the rays, for there to be a focal point, the rays must be coming from a center or a point from the lens. So that is where the focal point for the biconcave lens lies. Now how do we see objects? We see an object because light coming from it travels to our eyes as we view along a line at the object. That is the only way we can see. If light doesn't fall on it and hit our eyes, we can't perceive it. Similarly, we see an image for an object because light from the object reflects off a mirror or refracts through a transparent material, which is the lens, and it travels to our eyes as we sight the image location of the object. So that is how we see. Light from it comes from the object or is reflected from a mirror to your eyes or is refracted by a lens, hits your eyes, and we are able to see. But light must come from the object and enter our eyes for us to see it. From these two basic premises, we have defined the image locations as the location in space where light appears to diverge from. Because light coming from the object converges or appears to diverge from this location, a replica lightness of the object is created at this location. Alright, so essentially what they're saying is that once you see an object, you must get light coming from a focal point or from wherever the object is, whether it is real or virtual. But you must be able to get the light coming from that point wherever it is for you to perceive the object. Because remember, vision is all about perception. Now, constructing ray diagrams. And this is very important for persons who need to draw. To draw a ray diagram, we will have to recall 3 rules of refraction for a double convex lens. So this diagram shows now how you basically would draw a diagram where the object, light comes from it, passes through a lens, and then is brought to focus, either in front or behind. Now for the converging lens, it is brought in front of it. This is behind, rays are coming from, this is in front, and is brought to focus there. Now there are certain rules that must be followed in terms of drawing a ray diagram correctly. Rule number 1. An incident ray travels parallel to the principal axis of a converging lens, will refract through the lens and travel to the focal point on the opposite side of the lens. So what this means is that this, traveling parallel, will refract and then travel through the focal point, which is labeled F here. Alright? Second rule. Any incident ray travels through the focal point on the way to the lens, will refract through the lens and travel parallel to the principal axis. Coming back. So this now travels through the focal point, hits the lens, travels parallel. So before, parallel, hits the lens through the focal point. This one now, through the focal point, hits the lens, travels parallel. And the third one, any incident ray that passes through the center of the lens will in effect continue the same direction it had when it entered the lens. Alright, and we have here at the end. So, it comes parallel, hits it, travels to the focal point, continues. Comes here, goes to the focal point, hits it, travels parallel. This one now travels to the optical center, it goes through undisturbed. Alright? And once you have all the rays come into focus, that is where the image will appear. Alright? So the object is here, light travels from it, parallel through the focal point, through the optical center, unchanged, through the focal point, comes out parallel, where all those rays come to focus, that is where the image will appear. Alright? F here is just a focal length, or focal distance. Alright? Now, for the concave lens, or the diverging lens, is something similar. Light is refracted by a double concave lens in a similar manner that a virtual image is formed. We also learn about the 3 simple rules of refraction for double concave lenses. So rule number 1, any incident ray traveling parallel to the principal axis of a diverging lens will refract through the lens and therefore end up, let me just go to the diagram here. So essentially, this one that travels parallel will bend in such a way so that it comes to the focal point. This one that travels and hits the optical, this one that travels would want to point towards the focal distance or the focal length of the other side, but it doesn't, it travels parallel, so we have to backtrack it. This one goes through the optical center unaffected. So we have this one going this way, this one going that way, this one going unaffected. So when you backtrack, you get a virtual image because the rays don't come to focus here. Alright? So this will be made available for you, so don't worry yourself. Alright? So that's all for today, CSEC Physics. We hope you grasp some points on what we discussed.